Let's get started our final presentation. We are Team 9. The subject of our term project is the autonomous berthing of the ships using reinforcement learning. Contents are as follows: introduction, modeling, algorithm, and simulation result, and finally conclusion. Okay, berthing is the process of mooring a ship in a harbor. In this procedure, there are many things to consider, such as the position, wind force, and so on. To overcome these difficulties, tugboats are necessary to berthing. Autonomous berthing can reduce many accidents caused by human error. Here, we applied reinforcement learning to achieve that because it is difficult to express the dynamic model of tugboat and the ship accurately, and RL can solve many complex problems at once. Thus, the objective of the term project is as following. Firstly, we have to implement simulator using a simplified dynamic model. Second, we have to design reinforcement learning agent for control. And finally, we have to design theory-based controller to compare. First, let me explain how we built our simulation environment. We have to model a ship to berth and tugboats. We adopted 3 degree of freedom dynamics model. We set the state variable to have x, y, yaw, and surge sway yaw rate. Input to the system tau have x, y, n, which are forces in xy direction, and torque with z-axis respectively. They are generated by tugboats and mainboat surge force. We propagate system by adding x dot dt to the previous state. We consider tugboats as forces exerted with angle alpha. And torque force and system input tau has following relation. We put range constraints on torque force and its angle, and surge force of the main ship as follows. In RL problem, there are 2 kinds of learning scheme. The one is value-based method that we learned in class, and the other one is policy-based method, which is suitable for continuous action space. In policy gradient method, the policy is parameterized by theta. In the given policy, the goal is to find the best theta with respect to a policy objective function. Among many policy gradient algorithms, we use proximal policy optimization, in short PPO, because it is the state-of-the-art current RL algorithm with simple implementation and good performance. The algorithm consists of 2 networks. One is policy network and the other one is value network. For a policy network, we compute the loss values as follows, the last sentence, and the output of a policy network is the action value. Now, let me describe RL training framework in simulation. We have 3 big components here: RL network, gym environment, and simulator. The simulator is implemented based on Python-based module named Pygame. Here, RL network is the training network which outputs action, and it is trained using the given reward and observation. Here, OpenAI gym environment interface between simulator and RL network, and the reward is computed here. The input of network is observation values, which are the ship state, the distance error, and the velocity, and the previous model output. The output of network is the action values of tugboats and angle values between tug and ship. The reward function is shaped as follows. Distance and heading error is subtracted at each step, so as error decreases, the reward gets increases. A large value k is added to make reward positive to prevent the ship from going out of the environment boundary at early stage. And a reward for success alpha is added only when it reaches the goal state. And we normalize the reward value from 0 to 1. Now, let me explain how we designed the theory-based controller. We designed the controller in cascaded form. In the inner loop, velocity controller is designed with PI controller, and torque force allocator converts x, y, n to torque force with tangent angles and surge force of the main ship. In the outer loop, we designed position controller as sliding mode controller. As you can see in this formula, U is only controlled by x, and V are coupled each other, and are controlled by yn. And the first 3 loops represent the simple kinematics. Well, let me explain how velocity controller designed. U component PI controller is designed with following gain, so that steady state error for unit step input is 0. And due to the force constraint, we added anti-wind up controller here. And VR components are transformed to A, B, and Y and are transferred to V1, V2. So that A is only controlled by V1 and B is only controlled by V2. So the system is equivalent with below. Then remaining PI gain is tuned the same way with U component PI controller. And here, anti-window scheme is also applied. And here we have proposed position controller with sliding mode control using Lyapunov function. Given a fixed point x0 of f, Lyapunov function is continuous scalar function, which is locally positive definite, and only 0 at a fixed point x0. It is known that if time derivative of Lyapunov function is strictly negative, the fixed point x0 is asymptotically stable. In other words, x goes to x0. And we define Lyapunov function v as follows: the sum of squared terms, and setting UVR as following, we obtain strictly negative time derivative of v by calculation. Tugford's allocation problem is given by follows. Given tau, we have to generate f. We solve this problem minimizing below quadratic objective function j. We adopt its lengthiness variable s to prevent the situation which f cannot generate xyn due to the range constraint. We used fmincon MATLAB function to minimize above objective function.
This part is simulation result. Left one is the result of reinforcement learning. It is the simulation of the model with the highest average real value among the trained models. Learning was conducted for a total of 48 hours and approximately 10,000 epochs were trained. With this RL simulation, you can see that the model was quite well trained. The right side is the result of PID. If you look at the movement of the agent, you can see that it arrives at the goal point more stable than RL. From the simulation of the previous video, we plotted each trajectory, velocity, and heading as follows. It can be seen that the values from the trained model are not the same deterministic value, but various values. The reason is that it is policy gradient based reinforcement learning, which follows the mean and standard deviation value. To confirm the performance of the reinforcement learning, we decided to compare the PID control results. To compare the PID control, we selected one trajectory among 100 episodes. The agent with PID control moves rapidly at the beginning part and reaches the target point in about 100 steps out of a total 300 steps. There was also a little heading error. When looking at the trajectory, it can be seen that the PID control result is smoother than the RL result. Now let's compare the values for the control inputs. As shown in the figure, it can be seen that oscillation is larger for both RL and PID control method. If you look at the angle value of the tugboat, you can see that the RL output is under constraint. In this case, the constraint should be larger, or the amount of changing rate should be learned so that the model can be learned well. This is the conclusion. In birthing process, there is no fixed evaluation metric, so we compare the values, real value between RL and PID control. The average real value was not greater than the PID, but the error was not large. We interpret this result could be affected by whether model dynamics are considered or not, because PID is model-based and RL is model-free. So the performance of RL in this project is close to optimal. Reinforcement learning has the advantage that it can learn the action of the agent by the reward and penalty from the environment without explicit guidance. In order to confirm the usefulness of such reinforcement learning, it will be necessary to apply it to an application that cannot be solved by an existing algorithm. This is the end of final presentation. Thank you for listening.